Welcome to Study Loop.
Problem 718, a slingshot will shoot a 10-gram pebble 22 meters straight up. So here at the base, at the ground, we have a slingshot, and it shoots up this pebble up to a height of 22 meters. How much potential energy is stored in a slingshot's rubber band? That's part A. So we're told we have two different positions. We have when the pebble is in a slingshot and it's about to be launched, and then it goes up to 22 meters. So that's our second point there. So that immediately tells me that we're going to have two different points that we're going to assume have a conservation of energy between them. And so therefore we can just write out what that conservation of energy equation is going to be between those 2 points. So initially, we're going to say that we have y equals 0 here, so that the potential energy due to gravity here at the ground is 0. And there's no kinetic energy before it's launched. So all we have on the left-hand side of the equation is we're going to have the energy that is stored in that slingshot. The rubber band is going to be a Hooke's law, so it's going to be the elastic potential energy. And when the pebble travels all the way up to the top, there's no rubber band up there. We're going to assuming that there's no velocity there. So that means that we're going to have only gravitational potential energy there. So that's going to be the two elements of this equation. And let's go ahead and write down what we know. What we're going to find is the potential energy stored in a spring. So this is actually what we want to have in the end. This is what we're solving for, the potential energy of the slingshot. And that's going to be equal to the gravitational potential energy. And I'm just going to immediately substitute in what that is. So that's mg change in height. And that's going to be 10 grams is 0.01 kilograms times 9.81 meters per second squared times our change in height. We go from 0 to 22, so that change is 22 meters. And that's just units and multiplying numbers. So that should just give us 2.16, and the units are joules because it's energy. Okay, so that's part A. We have the potential energy that is stored in the slingshot is 2.16 joules. Now we're asked in part B, with the same potential energy, 2.16 joules, stored in a rubber band, how high can a slingshot shoot a 25-gram pebble? So again, we're just flipping this around. We're going to have U elastic equal to U gravity. So we have the potential energy that is stored in the spring initially is going to be the same, but we're using a different pebble. So I'm going to write 2.16 joules is equal to mass times gravity times change in height, but we're going to have a new mass, so that's going to be 0.025 kilograms times 9.81 meters per second squared times our change in height. And so that is just going to be some more calculation. We divide both sides by the mass and gravity, and that should just give us a height, a change in height that is equal to 8.8 meters. Okay, so C, what physical effects did you ignore in solving this problem? So there are a number of factors that you have to assume or disregard. So first off, we have that the assumption that there's going to be conservation of energy between the slingshot and the point at which the pebble reaches its peak. So first off, with the slingshot, we are assuming that all that potential energy is converted into kinetic energy. So that's our first assumption, when in reality, the slingshot will also heat up a little bit, will absorb some of that energy into its molecules, and it'll heat up a little bit. So that would be some energy lost as the pebble leaves the slingshot. Also, we have air resistance as it travels through the air here as it moves from the bottom to the top of its arc. That can vastly affect the projectile of the particle. And then additionally, we also have the fact that this rock is assumed to not be tumbling, it's not spinning at all, so that could be another factor. And overall, there are some things that we just assume that are going to be not a problem when we solve this problem. So that's a good discussion